Thanks very much for the organizers for having me here. When I got the invitation is about quantum optics and the quantum materials, and I thought both are topics I'm very interested in, so of course I will come. Then I received this wonderful list of intriguing questions, and I realized there's almost nothing I have done that I can contribute. But that also makes this conference irresistible to me. So here I am, and deciding still this morning what to talk about. So what could be relevant? Where there are quantum correlations, there are a couple systems that I worked with that there are quantum correlations, although not quite the type perhaps this community is trying to figure out. And how to measure them. I know how to measure them through coherence functions. And I look forward to learn a lot more from this conference, how to measure them in more exotic settings. But that's what I have worked on, so that's what I'll talk about. I guess I'm next to last of this very long, intellectually stimulating day. So I guess I have an excuse to give you something a lot easier to understand and relatively well established. And as a small break before we have the finale of the day. So I worked a lot with polariton condensates in gallium arsenide polaritons, and more lately with the 2D material polaritons. So I will put together some things that might be relevant, sort of as a foot of sorts, to see what can have some cross-fertilization among the topics that have been intensively studied at this conference. So apparently this is a long list, so I won't go into details of any of them in the hope of spreading out and hopefully find some common interest. So we'll start with a very brief introduction of polaritons, just so that we're on the same page. So we heard about the polariton strong coupling already in the previous talks, so excellent introduction. And they're basically, so I will basically focusing on exciton polaritons. They're electron hole excitations, that's paired excitations strongly coupled to light in the regime where the coupling is much stronger than the decay or dissipation. And so they form those new eigenmodes of polaritons that are linear superpositions of the excitons and the photons. So they have a nice properties coming from the exciton part and those from the photon part, especially the flexibility to engineer the modes and to probe and detect the properties of the system. So one of the best things about the system is there's in this strong coupling regime, since photon is part of the polariton mode, we have a one-to-one mapping from the polariton properties inside to the photon properties that comes out from the cavity through the cavity leakage. So that gives us a direct way to map out the dispersion relation, the statistics, as well as the coherence functions of the polaritons. And one quantum states, macroscopic quantum state can form is a condensate. One way to create that is basically excited, let it thermally relax. And the polaritons or the cavity give us a way to create this dispersion with a very small effective mass. So it's relatively easy to reach very high phase space density once we can overcome MNI thermalization bottleneck. Then we can get to the bosonic degeneracy limit, and that triggers stimulated scattering that builds up spontaneous coherence, and that gives us a polariton condensate or a polariton laser in a dynamic form. And a huge amount of work has been done on that. I will not go into the review of that, just to give a quick example of how such a system is made and works. And here's an example where the cavity is made with two mirrors. The bottom is called a distributed Bragg reflector. It's a stack of low and high refraction index layers. And there is a cavity layer somewhere. And we can put active materials inside that forms the exciton layer. Then in this case, we use a top mirror, which consists of a 1D grating. The grating acts as a high reflectance mirror, but it gives us a number of design parameters to control the modes of the polaritons. For example, if we make it a finite size, we can get a finite size effect of quantum confinement, lateral confinement of the polariton mode. That's the polariton modes we get over here. They're fully discretized because of this lateral confinement. And it has a grating that breaks rotation symmetry. So we have very strong linear dichorism. In one linear polarization, we have polaritons. In the other, we have just excitons. Now, if we pump the system, and we start from a highly non-equilibrium distribution due to the slow thermal relaxation, until we start to get enough population in the ground state that triggers the stimulated scattering, makes it to build up very rapidly, very much like a lasing transition, or that's basically the stimulated scattering threshold, or the condensation threshold, or the lasing threshold that can be seen directly from the input output. Then we can characterize its coherence functions. So that can be directly mapped out through the photon field through first order and the second order coherence, as we heard wonderful introductions already on that. So the first order coherence we can measure through a microcell interferometer interference. And here's the example of the time domain microcell first order interference, which we should have close to 1, except for experimental imperfection at 0 time delay. And as we change the time delay, that decreases, the fringes blurs out, and that maps out the G1 tau function. And we can define where it a certain coherence time, such as 1/e decay time. What is interesting in this polarity condensate is that there is interactions between the polaritons after all. So while the coherence increases very rapidly above threshold, following like a photon laser of the charlatan limit, at a higher occupation number in the condensate, it starts to decrease. And at the same time, the line width or line shape also changes from a Lorentzian line shape to that of a Gaussian line shape as a result of the interactions between the polaritons in the condensate. And this transition basically happens when the total interaction energy becomes comparable or larger than the decay or the line broadening of the intrinsic line broadening of the condensate. So that has been modeled very well for atomic laser theory, although it's much easier to implement and measure that in the polariton condensate, where it shows through as a result of the interaction, in the low occupation with the weak interaction, we have a charlatan laser limit, where with high occupancy, we get to this line broadening, Gaussian broadening limit. And in this case, we get to this strong interacting limit with an occupation of about 1,000 polaritons in the condensate. So that's the first order coherence. And what's the second order coherence? Does that affect the second order coherence? And that we measure through this Hambry-Bound twice type of a setup, basically split and the dual coincidence counting. As we know, it is for thermal or chaotic light, it should be 2. And for a perfectly coherent state, it should be 1. And anything below 1 is quantum light with quantum correlations. So indeed, we see that at below threshold, we have bunching, and above threshold, it decays very rapidly to the Poisson limit of a coherent state. So there is a teeny bit of oscillation, but given that, and sometimes it seems to dip below. So given the uncertainty, we cannot really say much. And that theory before also suggested a G2 that is bounded by 1 for perfect coherent state, where the interaction in the sense broadens the line and also degrades the second order coherence. Sorry. So here it is, the saturation density depends on the interaction, while the occupation number increases, we approach the Poisson limit. But one could ask the question, when the interaction is very, very strong, we should go to the polariton blockade region. And there we actually should have very strong anti-bunching. And in between these two limits, as we crank up the interaction, should we actually expect a squeezing in this system? And that could be an interesting question. We are sort of limited by how much more we can push that. So we didn't pursue that further, but I think with the development of materials and the cavity quality, it now actually become a more relevant experimental question as well, and hopefully interesting theoretically. But polariton blockade has been studied and pursued and actually achieved in some sense, but not in the condensate, in the true single polariton blockade limit. That's shown in these two papers. Both of them used a single quantum well to maximize the saturation that gives the effective interaction. And both of them used effectively a fiber cavity to reduce the lateral motor volume and maximize the collection efficiency in order to measure this finite amount of anti-bunching. That's sort of what one can push to with a gallium arsenide polariton system, and that's still the best has been reported to date. But I do want to make a small advertisement of our recent work in collaboration with Professor Roland Rappaport at Hui Deng University in Israel, where they have developed different type of a polariton system, which is essentially a waveguide polariton with a bottom mirror to improve the coupling. And so the waveguide geometry allows very easy electrical control of the system. And we used a wide quantum well so that when we apply the electric field, there is actually a finite dipole moment. So we have, in that sense, a dipolar polaritons. So dipolar polaritons has been sought out to enhance the interaction through the long-range dipole-dipole interaction. But the enhancement is essentially a factor of 4 or 5-ish, or at most order of magnitude. So it wasn't enough to really push it into the polariton blockade regime, in addition to a lot of additional complications coming from having electrical control. But surprising, and most of the time it's using two quantum well, a double quantum well structure to impose a permanent dipole. What we found quite surprisingly is that in this system, in a single wide quantum well, there's actually a much, much stronger polariton-polariton interaction compared to predicted for a double quantum well dipolariton system. And we actually managed to measure a finite anti-bunching in a not so well confined system, and probably can improve a lot if we create a confined system to reduce the mode volume. Sort of intuitive understanding we get is it turns out being a single quantum well with a dipolar, with a dipole, the dipole depends on the electric field. And the addition of another exciton actually screens that electric field. So this self-screening effect turns out to give a stronger shift or stronger sort of saturation effect compared to energy shift compared to if we use double quantum well and fix the size of the dipole. So perhaps this is one way we can push to a stronger interacting polariton condensate and study some physics there when correlation may become relevant, or strong correlation may become more relevant. So that's basically a single polariton condensate. And but this is a system where we can easily engineer the mode, so we don't have to limit to a single condensate. If we create a coupled condensate, for example, if we make 2 of them, we would expect a Josephson coupling, and that will splits the mode for the symmetric bonding mode and anti-symmetric anti-bonding mode. And that has also been measured in various structures. And in our grating mirror structure, we can implement it quite easily by changing slightly the air gap thickness. And that gives a potential double well for the polaritons. Here's the real space wave function for the bonding state, anti-bonding state, and that's the K-space wave function for the bonding and anti-bonding state. So if we zoom into these two coupled states and pump it, below threshold, we have the standard mode profile. High pumping intensity, we get lasing in the bonding state or the ground state, as expected. What was unexpected is that in between, new frequency modes appeared. That is not the bonding, neither the anti-bonding states, but really new states that came out from nowhere. And it's also roughly periodic in spacing. So if we look at the coherence property of this system, if we look at the whole, it's very similar to single condensate. If we look at the relative phase coherence between these two sides, however, those most new frequency in between has a phase difference between the two sides that's different from 0 or pi, or it's different from that of bonding or anti-bonding states, but something in between. And turns out the theory that could explain that is that it formed a limit cycle in this system. And because of the dynamic instability introduced by the coupling dissipation together with the interaction. So one way to model it is basically those coupled modes, since they're dissipative, they actually have a different dissipation rate. It turns out the anti-bonding mode at high energy could have a lower dissipation rate, and that presents a dilemma which one the system really wants to condense into, and that leads to the stability and the spontaneous bifurcation of the modes and oscillation as a result. So that can be modeled by a coupled mode theory as well. And you may call it a time crystal, a classical time crystal. And that is basically a prelude to the chaotic, to chaos in the system. So if with the tuning of the parameters, we can maybe implement a very rich phase nonlinear dynamics phase diagram. So of course, the question is, in those coupled systems, in principle, they could form a model for two-mode squeezing, and where the entanglement, where there will be finite entanglement, and whether or not we can achieve that in such a bosonic condensate, coupled condensate, as we increase, especially as we increase the interaction between the polaritons. And whether or not there are many-body entanglement in this dynamically unstable and strongly interacting system. Those are all very open questions that perhaps it could provide some sort of a model system to explore these questions. So besides BEC, there are other phases that can exist in the polariton condensate. For example, we know that in 2D, infinite 2D system, there is no long-range order. So Bose-Einstein condensate should not have existed. And we have it only because we always have a finite size system. However, as we increase the size, we would expect the BKT transition in the 2D system that's driven by the vortex physics. So that has also been studied, and that's measured by the power law decay of the coherence of the order parameter or the coherence functions. So in many of these experiments, the size is not well defined. It's basically phenomenologically defined based on the theoretical experimental conditions with the pump and the decay length or the propagation length of the polariton condensate. So if we put a more well-defined sized system, for example, we can use a ring pump to create effective confinement ring potential for the polaritons that give a system and then increase the size and see when we start to see the transition from BC to BKT. So when we tried that, we didn't quite go to a big enough size to get to BKT limit. Instead, we found something also at first puzzling. And again, below threshold, we have quite a non-thermal distribution. And at a certain point, all the population essentially condensed into a very narrow energy bandwidth, and very much as one expects from a condensation phenomenon. But that's not the ground state. Here's the zoom in of the bottom part. So it's not the ground state, but within KBT of the ground state. It's not really a thermal relaxation bottleneck either. As we increase the pump more, somewhat slowly in terms of increasing the power, this mode spreads out to many different energy modes and eventually does condense into the true ground state of the system. But only in what we can resolve in our spectral resolution and spatial resolution. If we look in time, in the first order time coherence function, however, this seemingly innocent simple ground state actually had a two-step first order coherence functions that suggested is not a simple condensate. And if we try to find out the shape of this coherence function, one is basically a Gaussian decay as expected from interacting condensate. The other follows very nicely a power law decay. So what happened, we believe, is we first get a localized quasi-condensate because we have this potential and the relaxation of the population from the edge toward the center. So at somewhere along the way, at a locally it condensed into the local ground state, but not the global ground state. That takes a while for it to condense into. And in the global ground state, there is actually still phase saturation because of this dynamics in spatial inhomogeneity between the BEC and the BKT phase in the system. Sorry, I forgot to add the coherence time. If you look at it, this is limited by the time window. From the fitting, the coherence time basically increases by 3 orders magnitude through each transition to the localized BEC to the BKT phase with the quasi-long range order. So the last phase I will talk about for the polariton condensate is if we keep increasing the density. At a low enough density, we can approximate excitons as a weakly interacting boson. And as we increase in the density, however, the electron and holes fermionic nature will have to show up as we start to go toward the transparency condition and even go above it toward the Fermi degeneracy. And if we stay at a 0 temperature, no defacing and no decoherence, so in the low density limit, we should have a Bose-Einstein condensate. In the high density limit, what we should have is basically a Bardeen-Kuiper-Schiffer type of state, where the pairing between the Cooper pair, the so-and-so Cooper pair is between the electron and hole, and the screen-Coulomb interaction naturally provides the pairing. But if there is dissipation, and most likely we're going to electron hole plasma. And that's typically what happens in the semiconductor as we increase the density. So it is very well known theoretically for a very long time. And transcribing it, extending it to the polariton case was pioneered by Peter Littlewood's group at Cambridge, where the polariton essentially also have this BCA phase for the excitonic part or the electron hole part, while the photon adding the photon part through the strong coupling. And of course, the polariton makes it much easier to measure experimentally as it enforces the coherence and makes it easier to directly probe the properties of the signatures of the BCA state. And in our case, we can take advantage of this linear dichroism where we have one linear polarization setting us into the BC or BCA phase, while the other linear polarization stay in the weak coupling regime that give us window to look at what happens in the electronic media. And that's where the distinction between BC and the BCAs exists. And so the The telltale basically comes from this essentially absorption spectrum, where we have a gain above the condensation threshold. And the spectral feature very much looks identical to that of a polariton BC, but in the gain of the weak coupling mode, we can see in the electronic reservoir, we have a finite fermionic gain, and that essentially defines a polariton BCAC state. So, and in the first and the second order coherence functions, however, we do not see any clear difference between a BEC phase and a BCAC phase. So in that sense, this different correlation in the electronic media did not show up in different spectral signatures, at least within our experimental resolution. Whether or not there is a difference exist, I don't know, maybe some of you already know the answer. So I think I will summarize the first part where this polariton system has a very rich phase diagram that gives us many types of different phases. So most of them are essentially in the weakly interacting bosonic condensate picture. And there is hope to enhance the interaction by a couple orders of magnitude, potentially, to push it into a strongly interacting limit, and maybe different new physics will emerge over there. I guess the advantage of the polariton system is that the properties is directly mapped into the photons as long as we stay in the strong coupling region. So the coherence functions, if they tell us something about the electronic correlations, they can be measured quite directly, experimentally. So how to push into some new regimes with the strong interactions and the more exotic properties? That brings me to the second part of my talk. That's a lot of what people here are also studying, which is basically van der Waals materials. So it turns out in van der Waals materials with a reduced dimensionality, the Coulomb interaction is stronger. The exciton binding is orders of magnitude larger, as well as the exciton photon interaction. And in a wide variety of those 2D materials, there is actually a very strong optical response, including some quantum materials, where bulk quantum materials, it's very hard to find one with strong optical response, but many of them in the van der Waals materials have such an interesting feature. So they provide a very nice system to start to use exciton as a probe, or to study how the interaction between material and the light as a way to understand or control materials, both in the strong and even in the weak coupling region. And also it has the flexibility to integrate with any types of structures. And that is particularly useful in terms of studying polariton physics with the 2D materials. For example, here we don't have to use those bulky fibropyro structure. We don't have to figure out how to make a grating mirror with high reflectance, but we can use the grating or generally a photonic crystal itself directly to integrate with the 2D materials. We simply need to place it on top. And it's so thin, so the evanescent field will already give us very strong interaction with the resonance mode of the photonic structure. So here's the early example where I simply put it on the grating, and we have a strong coupling even at the room temperature. It can also be extended to 2D photonic crystals. Here's a recent work by this very talented postdoc, Dr. Xie, who made those beautiful 2D photonic crystals and placed the TMD on top. And we immediately see a huge boost of the transport length, where the exciton transport is almost always limited to a fraction of the diffraction limited spot size, or a couple microns in the case when the transport is enhanced. But with the polaritons, we can easily go all the way to the edge of the photonic crystal of tens of microns. So, and it also not just limited to TMDs or normal semiconductors. but also some quantum materials such as chromium sulfur bromide, which is interlayer antiferromagnet, which turns out to have a record strong exciton oscillator strength. And that super strong exciton oscillator strength is very robust against excitation density or temperature until it hits the near temperature of the antiferromagnetic transition, then it is gone. So there is a strong correlation between these exciton modes and the magnetic order in the system as well. So in addition to create polaritons more easily due to the stronger exciton oscillator strength, the 2D materials also allow us to have to use light to manipulate the system with a much stronger effect. For example, with a very well-known optical Stocky effect, where we can dress a two-level system and then leads to a shift. We can tune the laser off resonance, so we will not create any excitation, but we'll still have a shift. And that basically forms the base of optical trapping in atomic physics. So in semiconductors, that has been studied for decades as well, except it's quite a perturbative effect. But in 2D materials, that shift can be much larger. And now we can also increase that shift by putting it into a cavity. For example, if we just put in a good old DBR fibroparallel cavity with a pretty moderate quality factor, we can already enhance the cavity field by 100-fold. And that translates to enhancing this optical Stocky effect field strength effectively by 100-fold. And here's just a comparison of the Stocky shift as shown by this twist here when the pump and the probe overlap on the DBR with a 4-fold enhancement of the field versus in the cavity. To get the same shift, we need 25 times less power. So that basically means about 100-fold enhancement compared to the vacuum field, compared to without a cavity. So that makes it much easier to cramp up the field intensity with basically a typical lab laser system, and also avoid heating in some respect. And the highest we could push to in that system is a splitting of 50 milliampere volt through this bicircularly polarized optical Stocky effect between the two valleys. And to get the same type of splitting with a real effect, with a real magnetic field, would require a field of a few hundred Tesla, and that won't be feasible at all. But this gives us a way not to, it's not a real magnetic field, but it serves the purpose of breaking the time reversal symmetry. And also can be turned on coherently, dynamically within femtosecond scale. And of course, it also allows us to tune down the field amplitude, but still have a measurable Stocky effect. And that may open a way to control the time reversal or do using laser control closer to the CW limit without burning the materials. So now that with the photonic crystals, we can directly control design the spatial symmetries of the system. And with the Stocky effect or with the laser control, we can control the time symmetry of the system. And combine these two, now we can maybe explore some other types of states in the system, such as topological states that requires breaking time reversal, as well as the special spatial symmetry properties. So I suppose topological states are, again, a type of states that may have correlations and interesting entanglement properties. So maybe that's one way it could be relevant to this discussion. So topological states can be found in various materials, and that depends on the lattice structure and the interactions in the material that we get. However, should have included. So, however, even in the in those work that sort of give a huge boost to the modern development of topological physics, they have proposed that we don't have to always use, for example, magnetic field, but can use a lattice structure, and specifically a magneto-optical photonic lattice to implement a topological insulator. And that has led to the experimental demonstration just a few years later using magneto-optical lattice, except those materials works at very low frequencies, or basically gigahertz frequencies, and as a result with a very tiny gigahertz gap. But that inspired a whole field of topological photonics to use photonic lattice structures to implement topological states. And there are roughly 3 types of those topological photonic states. And 2 of them only require manipulating the spatial symmetry. But the first one, which has a true topology or non-trivial topology, truly non-trivial topology does require time reversal breaking. And that is very difficult with photonic systems. Using magnetic optics is one way, but that's limited to certain materials and low frequencies. Using polaritons give us another way to implement that, where we can have the photon particle control the spatial symmetry, and using the excitons to control the time symmetry much more easily. And so there has been a series of theoretical work on that. And this one is probably the closest to the practical experimental implementation. And that is implemented in the gallium arsenide pillar array system. Here the lattice is created by those micropillars. And that also means that the lattice constant will be limited to a few microns. And that gives us a fairly small Brillouin zone that limits the band gap as well, and to barely enough to open, given the typical decay rates and the energy scales of the system. So the gap reported there is about 0.1 milliampere volts. And I don't think there has been any follow-up work or other work to show any logic gap or even to reproduce the result. So it's quite a heroic experiment. And that led us to look for other ways to open a bigger gap in the photonic system. So it turns out, and this type of topological gap is actually not confined to Dirac points at all, but is very widely existing in a large classes of photonic crystals. So essentially, any photonic crystal bands, a lattice bands, with the symmetry protected degeneracy, will may be used to open a topological gap. If we break the degeneracy by breaking the time reversal symmetry. And the most common type would be the quadratic touching. And those quadratic touching points exist at gamma points as well, rather than the K and K prime points, which is often below the light line and very much harder to access for optical experiments. So with those quadratic touching bands, and there is a phase winding due to the symmetry properties of the lattice. So when we couple it with the excitons and break the time reversal through the excitons, that will open a topological gap. And there are many parameters we can tune with this lattice system to optimize the gap and enhance the gap. And the gap size is not, and the Brillouin zone can be much larger in this case, as we have a spatial period on the order of a fraction of a wavelength. So the gap size can be orders of magnitude larger compared to using micro-sized pillars. Using realistic materials, we can get a gap of over 10 milliampere volts in this system. And their Berry curvature will also be very different compared to that around the Dirac point. And that Dirac point is highly peaked, but in this case, it will have a singularity at the gamma point, but it has a ring-shaped structure. So whether and how it will map into so they will have different quantum geometric properties and how they will map into an entanglement of the particles if we have correlated particles occupying these bands. I'm not sure, I guess that's maybe another open question one can look into. So another type of these topological bands can be implemented in the different type of lattice with those symmetry protected bound state in continuum. Bound state in continuum are basically a continuum band where there is a single state that is forbidden to couple radiatively due to a symmetry constraints. And sometimes there are accidental BIC, but for those symmetry protected BIC states, if we break the time reversal there, break the degeneracy there through the break the time reversal symmetry, then there will be a winding between the photon and exciton coupling. And the winding comes from the polarization vortex around these BIC points. So that's another way we can open topological gap in the polariton system, even within the light cone at the gamma point. So here's the one example how we can open such a gap. It's also a way to get a higher order term bands much more easily. If we find a higher order BIC point, then that when the gap opens, it will have a higher order term number in the system. So basically, this gives us a different recipe to create a polariton chain insulator. And there's a collaboration with the Professor Kasun's group at Michigan. Essentially, we use the exciton to break time reversal, but use the photonic lattice and exciton photon coupling to produce the winding and generates the topology. We can do it at the Dirac points with certain limitations, but we can do it in a much larger class of photonic crystals at the gamma point with a symmetry protected quadratic touching, or at a symmetry protected band state in continuum states. So I guess going to the very last part of my topic. So those topological bands in the single particle picture, they still don't really have non-trivial entanglement. And if we have interacting states occupying those bands, and then they'll create edge states and excitations that indeed may have non-trivial many-body entanglement that we can measure in the polariton system also quite directly through the photon mode. And to get there, we need to increase the interaction. With the gallium arsenide system, there are ways, but with the 2D material system, in principle, there are broader possibilities to increase the interaction. And one possibility is to make use of the Mori lattice. Mori lattice basically gives us an electronic confinement on the nanometer scale, which matches quite well the Coulomb interaction scale. And each of these Mori cells can function quite well as a quantum dot. And then quantum dot basically has the strongest optical nonlinearity in semiconductor systems. So interestingly, as we couple such a quantum dot array with a cavity to form polaritons, and even though the polaritons, the photon mode couples collectively to all these quantum dots, Mori quantum dots, the quantum confinement experienced by them still manifest in the enhanced nonlinearity of the resulting polariton mode. An intuitive way to see that is basically here in this system, we can replace the length scale of the exciton Bohr radius by that of the quantum dot size as a length scale to give the interaction length or scattering length. And that can be 10 times larger than that of the exciton Bohr radius without compromising the exciton and the photon coupling strength. So another possibility may be to use quantum materials where maybe the interaction properties will be quite different than what we're more familiar with in simpler semiconductor systems. And chromium sulfur bromide is one such material with a very large exciton oscillator strength to begin with. They have a high saturation density, but disappears, as I mentioned before. And in those systems, we can also try to create a Mori system. If we create a twisted bilayer of those chromium sulfur bromide, it turns out the exciton energy has an interesting dependence on that twist angle. At a bit larger twist angle, the exciton energy increases, and we could model it very well, shown by the solid line, basically based on two uncoupled monolayers, but with a twist-dependent dielectric anisotropy. If we account for the anisotropy induced between the two layers, we can explain this dependence of the exciton energy. At very small twist angles, however, the dependence is just the opposite. And there is a magnetic field dependence as well. They have a different energy at 0 versus a finite magnetic field. And so for this system, that basically suggests there is actually spin coupling between these two layers. There are two uncoupled ferromagnets anymore, but may form antiferromagnetic ferromagnetic domains in the Mori lattice formed between these two layers. And then the question is whether or not there is such a spin correlation will also map into exciton, and in turn, the light that's probing those excitons are coupled with those excitons. So I think I will stop over there. There are some well understood physics and many open questions and how to extend them to something more exotic and interesting. Thank you for your attention.
We have time for maybe one or two quick questions. Dimitri.
Thank you for your talk. I believe you said that it's feasible to probe many-body entanglement systems. Can you elaborate on that?
Not quite. What I said is we can measure the coherence functions.
Yeah, I wanted to hear.
That's what you want to hear. If there is non-trivial correlation that can be mapped into correlation functions, then we can measure those correlation functions quite directly and easily in the polariton system.
If I may ask, actually, so you showed this collaborative work with Ronan Rappaport on these dipolar excitons, and you mentioned that it should be possible with confinement to bring that system closer to kind of to the photon blockade limit. So how close do you think you can get actually? What would set the limit on how close to single photon nonlinearity that system gets?
Yeah, that's a great question. I think in reality, we just have to find out in experiment. So if we based on the wider waveguide and the amount of blockade we get, which is 0.05 anti-bunching, and it would translate to a blockade radius of 4 microns, which is huge. Which means if we confine it to say 1 or 2 micron, which is very easily doable, then we should essentially go to full blockade region. But I'm sure when we actually do it, there are other complications that come up.
Well, I'm very excited to find out what happens. Any last questions? If not, we can move on to the last speaker of today. Thank you again, Hui.